you don't need to see the chat. And there we go. All right. So welcome to our AP Physics 1 and 2 review session. Although here we're probably most going to do Physics 2 because there is a lack of people in Physics 1 in the chat. All right. So the agenda that we're going to go through today is first we're going to talk about the exam format for each exam, but we're probably mostly focused on Physics 2. Then we're going to go through key tips, then maybe go through a practice FRQ, and then you have any questions at the end. Right. Now let's just exit out of here, and I'll pull up the Physics 2 course right here. So Physics 2 is slightly different from Physics 1. And I'm actually talking about the exam format as well. If you've taken AP Physics 1 last year, you know that let me pull up the exam. The exam was 50 questions. Yeah, it was 50 questions in 90 minutes, and then it was 5 questions, 5 FRQ in 90 minutes. But for Physics 2, for some apparent reason, they have 4 questions for the FRQ instead of 5. I don't know what the decision behind this is, but yeah, I'll take one less question in the same amount of time. I'll take that anyway. So here you have 50 questions in 90 minutes. And that's 50% of your exam score. Oh, and there's also these multi-select questions too. I just remember this right now. So there's 5 questions where you have to choose 2 answers. And if one of your answers is incorrect, if any part of the thing is incorrect, you don't get the point. You have to choose both of the correct answers in order to get the point for those questions. But it's only 5 questions. I would not really stress about that too much. Now, the second section that we have is a free response. So we have 4 questions. It's an hour 30, and that's also 50% of your exam score. And to be honest, I think this is where I clutched my points for the exam. I don't think so I did super well on the multiple choice. But here you have 4 questions, and it's good to know the different types of questions. So you're always going to have that experimental design question. And with the experimental design question, you're going to set up an experiment. They'll tell you to like write a procedure. And then with the experimental design, you have to figure out, okay, what equipment are you going to use? And how are you going to measure the quantities that you're going to measure? So let's say you want to measure time, for instance. Then you also be like, okay, I'm going to be measuring time using the stopwatch. Or they'll be like, okay, I'm going to be measuring distance using a meter stick, for example. So you got to say what you're going to measure and what you're going to measure that with for the experimental design. Then here is the quantitative qualitative translation, which is honestly one of my favorites. It's basically you have they give you like an equation sometimes, actually a lot of the time. And what you're supposed to do is like, okay, suppose if one of these variables like doubles, or it's like one of these variables triples, what happens to the overall result? So they'll give you an equation. It'll be like, okay, does this satisfy, like based on your knowledge of physics and like the laws of momentum or the conservation of energy, something like that. Do these equations match up with the reasoning that you have? And yes or no, like why? And with the QQT, I think that's what it's based around. It's like some math, there's very little math on the overall exam if you've taken Physics 1 before. But in Physics 1 and Physics 2, very similar in terms of like there's a limited amount of math in the entire exam. But yeah, there will definitely be like analysis between different equations and trying to figure out, okay, how does this relate to that? That's what the quantitative qualitative translation is. And then, okay, the short answer paragraph argument. Okay, let's talk about the short answer first. The short answer is basically, okay, just figure out a bunch of stuff. I don't think so it takes too long. But the paragraph argument, this is going to be like your longest response, pretty much, where there's not that much parts to this exam, sorry, to this short answer, but there'll be like one specific questions like in a coherent paragraph, write down like your reasoning as to why this works. So this is going to be like the most lengthy one, and you have to come up with like a claim, evidence, and reasoning, like you do in like AP World or like AP Lang, for example. But you'll be using physics concepts instead. So that is the short answer paragraph argument. So we've gone through all the different types of free response questions over here. I think that's the exam format. So let's just go on to what is it? The CED. All right, Physics 2 CED. Unit guides. No, not the unit guides. Course at a glance. There we go. Okay, so first we have one of our favorite units, fluids. Why do we like fluids? Because it's one of the easiest units in Physics 2. Here you're going to be talking about density. Know that density is a property of a material. So for example, if you have a copper coin and you have a copper mountain, like you don't need to know the sizes of all of them. You need to know that, okay, the density of the copper coin and the copper mountain are exactly the same because they're both made of copper. They take up the same amount of mass per volume, so they have the same density. Oh yeah, pressure and forces. What is it? I think it's F equals rho. Yeah, pressure is rho times A. So understanding forces. So it's basically going back to physics one, tying in Newton's laws, except now you're having this pressure and area component as well. So then, yeah, you have free body diagrams. Buoyancy is basically an upward force that opposes gravity. The conservation of energy, very crucial to bring that back from physics one, seeing how energy is conserved in fluid systems where mass is not particularly in one place. Oh, that mass flow rate, that was a very interesting one. But it's like mass flows at an equal rate. It's not like the same, different masses flow at different rates. So that's fluids. Does anyone have anything else to add with fluids? Something? Oh yeah, conservation of energy. That's Bernoulli's principle, and that takes let me bring my handy dandy whiteboard. And for that whiteboard, I also need okay. I think I got it. So, okay, we all know that mechanical energy is conserved, right? In a system where there's no net external forces being applied, yeah, mechanical energy will be conserved. All right. So in mechanical energy, in this case, is going to be kinetic energy, and it's going to be potential energy. So here that means the kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. So, okay, if we break that down, that's kinetic energy is half mv squared. Okay, and I'm writing with the mouse. I probably should be doing that. Give me 1 second. Okay, I guess I'm stuck with the mouse then. Okay, so kinetic energy is half mv squared, and then potential energy is mgh. Yeah, I'm just going to be like initial, like 1 or something, and then the kinetic energy is half mv squared of 2 plus mgh of 2. Okay, then now if we do a very fascinating thing, and we divide everything by volume, right? So we divide everything by volume, then what we get is mass divided by volume, right? That's nothing but rho, or density. So then basically now we have this equation of half rho v squared 1 plus rho gh1 equals half rho v2 squared plus rho gh2. So then here we got this is Bernoulli's. And at this moment, I actually found my pen. It's going to be a lot easier. So this is Bernoulli's principle right here. And oh, I remember. Does anyone know off the top of their mind the mass flow rate equation? Isn't it m1v1 is equal to m2v2, something like that? Does it look like familiar?
There was a Q in there. I'm not sure.
There was a V. No, a V and A.
Because M equals to PVA.
Oh, sorry. Yeah. It was mass times this.
Was it
Let
better
me-
mass?
It wasn't VA is equal to VA.
Yeah.
Oh yeah. There we go. Okay, this is momentum. Like so.
Yeah, that's why.
Yeah, A1 V1 is equal to A2 V2, and then yeah, there's like a I think it is derived from momentum though, actually, because yeah, I think it is. I don't know off the top of my head why that is the case, but I think volume, because a certain mass, it travels over a certain area per time. So then it'll be like, there's something. Oh, it's like pressure. It's like, if like M1, it's like momentum of that mass is conserved, right? Then we can be like M1 GV1 is M2. And then that's a specific pressure. Yeah, then I think that's specific pressure. So you can be like PVG. Okay, actually, I don't want to get into the details of this. Just know that this equation exists. And I suggest going and understanding the proofs of why these work the way they do. Unfortunately, in these sessions, we can't really cover like why things work the way they do here. But this equation can be used with this equation, and you can find a bunch of values from it. And I guarantee there's at least going to be one question on the EP exam that takes this mass flow rate equation and puts it into this Bernoulli's principle, and you're going to get something out of it. I highly guarantee. So because I remember there was one like that on practice exams, and I remember doing it on the AP exam last year as well. So this is something to be on the lookout in terms of fluids. I think that's the biggest thing. Other than that, everything else is like pretty self-explanatory in terms of like physics 1. All right, let's move on to unit 2, just thermodynamics. And I should also just state the difference between physics 1 and physics 2, in my opinion, is physics 1, everything builds together smoothly, whereas in physics 2, things don't really build off each other. So like fluids is basically fluids. You can't really mix up fluids with like electricity. That would be a really weird question. But yeah, so unit 1, that's fluids remains on itself so that you can really identify easily what types of problems to solve. So yeah, whenever you get a fluids question, you'd be like, oh, it's fluids, and then you pull up your toolbox of fluids. The same thing with thermodynamics. And I actually, thermodynamics is tested more on the EP exam than fluids. So let's just look at this right here. Thermodynamic systems. Oh, it's like, okay. Everything's just coming back to me now. So we have, there's 4 ones, right? There's isothermal, adiabatic, isovolumetric, and isobaric. There we go. So these 4, isothermal is the change in temperature is equal to 0. Adiabatic means the change in heat is 0. Isovolumetric is the change in volume is 0. And isobaric is the change in pressure is equal to 0. There. I think so. Does anyone have it? Am I messing up anywhere here? I think this is right. All right.
You're good.
I think sometimes they use like isochoric or
Yeah, isochoric. Yep.
I think
Iso.
same thing though.
Isochoric, really?
Yeah, I know it's weird. So that's why I like to say isovolumetric. But
Yeah, you know, like what you mean.
okay. And then yeah, let me put this to one side and I'll put this on the other side. So yeah, just know each of these systems, and then how this will be helpful is on the, let me pull up the EP physics 2 formula sheet. Right there. Over here, there's, let's see, the bunch of thermodynamics. There we go, thermal physics. Oh, I should have just pulled this up. Okay, yeah. Should I just cover second law of thermodynamics here? Okay, I think I just should. So the change in energy of the system is the heat, the change in heat over, yeah, the energy transferred by heat. So this is just heat transfer, and then work. And then, yeah, internal energy of the system. Okay. So I'm pretty sure this is the second law of thermodynamics. Yeah. Thermodynamics. Or that might not be the second law. I don't know for sure. I know there's a zeroth law. The zeroth law is like, is it equilibrium? It's like heat travels from high to low. That's what zeroth law is. I don't know, might be second, but it's definitely a law of thermodynamics. Let's just say it's a law of thermodynamics. And you can use this equation to your advantage when you have adiabatic systems, for example, you know that heat transfer is 0. So then you can say this is 0. And then therefore the work done on a system is directly impacts the internal energy of the system over here. And isovolumetric, what is it? Work is equal to negative P over V something, right? So let's say something is isovolumetric, the volume stays constant. Then over here, then the amount of work done on the system, because, oh yeah, if you, let's say we have like a cylinder of a bunch of stuff, right? In here, like we have a gas, and if it's being compressed, then the volume changes, right? And the change in pressure, so pressure times volume. If you actually, there's actually a neat way to do it. This is just another way of work, right? Because work, if you remember from physics 1, is force times distance. You apply a force onto some sort of distance, and that is work. But then force is basically another way of saying pressure times area. If you apply a pressure over something, and if you take pressure over area, that's force. The force, and then you have this distance over here. But then now you can do clever manipulation and be like area of some circle multiplied some sort of distance. That's a volume that's being covered. So that's the thing, like so the change in distance, I should say, force times the change in distance. That would be similarly, that would just be pressure. I don't know why I'm saying rho. This is P, pressure times the change in volume. So whenever you have something like that, then you have work. And there's a negative sign over here. I know that because there's a positive change in the volume, right? Let's say it expands. The work is opposing the distance travel is opposing the force. So what is it? The gas particles. Okay, I don't know what exactly it is, but like when it expands, there's negative work being done on the system. And negative work means that the force and the displacement of the gas particles are in opposite direction. And what's happening when you're decreasing the volume, when you're compressing it, when you're getting smaller and smaller, then you're working, the force applied is being the same direction as the displacement. So then therefore you would have, yes, no. Okay, let's see. I just need to draw this more. Oh yeah, okay, I get it. So the gas particles, let's say you're expanding right over here, right? This one is like, it goes this way and this way. So if the gas particles are pushing this way and so then there's less work being done on the system, or like there's negative work being done on the system. So then, okay, I'm just confusing myself too much, but just know that there's negative because when you're increasing the volume, there's a decrease, a negative work being done to the system. And then vice versa, if you're decreasing the system, then there's positive work. But anyways, you can use this at your advantage and then you can plug it into right over here. Yeah, let's just move on. So thermodynamics and forces, I mean, it's very similar to like physics 1 and like how you just draw free body diagrams, apply similar ideas. Heat and energy transfer, internal energy transfer. That's what I was using the second law of thermodynamics, right? So we use the equation over there and just try to plug in whatever you possibly can. And then based on that, you can manipulate stuff. Oh, and there's also conservation of momentum. That's actually pretty cool. Just remember elastic collision from physics 1 is when kinetic energy is conserved. And usually in thermodynamics, we assume that's the case, but in real life, it's not always the case. So then, see when we go over here, we realize that I think this is where we can figure it out. So kinetic energy, this is the kinetic energy of particles right over here. When they collide into each other, this would be conserved if it's elastic. So notice the K over here, which is thermal conductivity, and then temperature, and then what is it? So if it's an elastic collision, then these are conserved, and if it's not an elastic collision, then this quantity will not be conserved. So that's something to look out for over there. Thermal conductivity does not appear on the AP exam too much, but that is this equation right over here. So honestly, with a lot of equations in physics too, you just have to see like, okay, if we increase the temperature, then we're increasing the amount of heat per time, essentially, right? Whereas like if you're increasing the length of the bar, then like, the thermal conductivity of the bar becomes less, right? So you have to make those connections there. Just see like, okay, if you increase area, what happens? If you increase temperature, what happens? You don't necessarily need to know like why everything is the way it is, but like if you just manipulate this, it'll be like, okay, we increase temperature, this is what happens. Or we decrease the length of the bar, that's what happens. So that's thermal conductivity there. This one, entropy, that's not really covered that much on the exam, so I wouldn't really worry about it. Oh yeah, I forgot one more thing. I forgot PV equals nRT. I should have discussed that. PV equals nRT. So this connects pressure, volume, and temperature together. So this is a very important equation in physics too, in connecting pressure, volume, and temperature together. So, and if you have a change in the temperature, that means you're going to have in, let's say, an adiabatic system, right? If you have a change in the temperature, then you're going to be having a change in the volume, which ultimately means that you're going to have a change in the work done, which changes the internal energy of the system. So you see how putting all these connections together, that's basically what you have to do for physics too. All right, let's move on to unit 3, unless you guys have any questions.
I did PV equals to nRT in chemistry.
Chemistry, yeah. So there's the connection from PV equals nRT from physics 2 to chemistry. With physics 2, what you have to do, you're not getting too into the details of the equation, but it's more like just relating, okay, if you increase the pressure, what happens to the temperature? Like a lot of physics is like understanding relationships between variables. So it's like if you held velocity, why do you call it velocity? If you hold volume constant, then if you increase the pressure, what happens to the temperature? Well, according to PV equals nRT, if you increase the pressure with volume being constant, then temperature also increases. So those types of relationships matter in physics too. All right, unit 3, which is the largest unit of physics 2. I was about to say physics 3 for a second. I'm like, hold up. But in physics 2, that's the largest unit over there. If you've done gravitation in physics 1, then electric force is very, very similar. Let me just, so everything has like an electric field. So let me just draw electric fields. So you have this, that. Okay, so electric fields go like this. When they point away from the system, that means it's a positive electric field. If they point towards, then it's a negative electric field. The strength of an electric field, that is K. Let's go back here. Okay, I don't remember those off the top of my head. And the thing is, you don't necessarily need to either. Again, physics is just knowing the relationships between variables, not memorizing the exact same thing. Oh, okay, so this is KQ r². All right, so basically, okay, we know from gravitation, right? So force of gravity. Okay, this is very basic, it's just mass times gravity, right? But in gravitation, that's basically mass times our constant gm over r², right? So this basically our gravitational field, let's call it GE times m, our mass, that equals to the force of gravity. Similarly, the electric force is equal to the electric field times, instead of mass, we're going to deal with charges. So electric field is KQ r². So electric field times charge, which is KQ r² times Q, that's going to be KQ². Or not necessarily Q², you just have like big Q, little q, because they can be different charges over r². And that's what electric force is at least. One thing to keep in mind is the force of gravity can only have one direction. So it only pulls, whereas the electric force can either pull or push, or it can have an attractive force and an repulsive force. There we go. So yeah, I've never seen the force of gravity push someone away from somebody else, right? But in this scenario over here, we have, okay, let's say we have a positive charge and we have a negative charge, right? Then what happens? They attract each other. Well, if we have a positive charge and a positive charge, they move away from each other, something that we don't see in gravitation. So that's something to keep in mind there. Let's move on. Oh, charge distribution. Oh, conservation of electric charge is the same idea as the conservation of mass. It's like mass can't be destroyed, created. Similarly, charge can't be like, destroyed or created from a system at least. So within a system, if like charges just get over here, they get distributed. So they just move around. And so if you have a loss of some charge from one area, another area is going to get gain of charge. So you can use it to your advantage. So you want to set something in equilibrium, then you can add or subtract charges here and there. What is it now? We have similar situation, friction, conduction, induction. This is how charge gets distributed to each other. I think friction is when two surfaces rub against each other and they transfer charge that way. Then what do we have? We have electric forces. They just repel each other, right? And then, oh no, I was talking about friction, conduction, and induction. Right? Conduction is like when two spheres, electric spheres, touch each other and charge being produced. Then induction is like the system from the earth, right? It like pulls electric charge from the earth and then releases it to the earth. So a charge can be distributed differently, but like the conservation of charge still like applies within a specific system.
Wait, does the test on like friction and like stuff equations like related to friction?
Oh,
Or-
like this type of stuff, like the UK stuff, the coefficient of friction stuff, or are you talking about
Or, but
something?
like electricity related to like electric charge related to friction?
I mean, there's for the AP exam at least, they'll be like, okay, two spheres are rubbing each other to, and they're providing friction or something like that, or like
Oh.
frictionally providing charge. That's what they refer to.
I see.
But yeah, that's the case over there. And then gravitation. Oh yeah, so here they're showing the differences or the similarities between gravitational and electromagnetic forces. Yeah, that makes sense. Vectors and scalar fields. I don't think that's super important. Electric charges in their fields, like, okay, how I showed here, anything pointing away from an electric field is positive. Otherwise, if it's pointing towards, it's negative. Oh, isolines. Do isolines show voltage, right?
Yeah.
Yeah,
I think
they
it's
like,
positive. Is it like a positive charge, and then if they're like negative voltages, is it negative?
yeah, I think
Or is it
that's
always positive since it's like, I don't know.
yeah, no, they represent potential energy essentially. Yeah, they represent potential energy. So the further away you are, essentially the idea is you have more potential energy from the charge. Like, or yeah, I think that's what the idea is supposed to be.
And yeah, it isn't like force like perpendicular to the isoline. Like I was a bit confused.
Oh, yes. I remember that particularly. Let's pull that up actually. Forces perpendicular to isoline.
Ooh.
Yeah, so yeah, these are electric potential. Wait, these are this is magnetism. Yeah, okay. I don't necessarily remember why it was perpendicular. Isoline and electric field. Let's pull it up.
I guess.
Wait, is that for electricity or is that for magnetism? But is there
That
no,
was
no.
for unit 3. Like I just remember unit 3 that I was.
Hmm. Isoline. Okay, that's something to keep in mind. I don't remember too many questions about isolines appearing on the exam, though. So yeah, that's a good question. I have to like remember. Okay, so here's like the distance away. Like, how would it go? Oh, is it because like the electric field is? I don't know for sure, but I think it's not a. I don't think so. That's huge. It's not a very like, small part of the exam. Okay, conservation of electric energy. That's okay. The same idea that we got from physics 1, right? It's like energy in a conserved system is going to be. Why did I say conserved system? Energy in a closed system is going to be conserved. So yeah, keep in mind that 75 questions for that. That's actually crazy. Well, okay, let's move on. Electric circuits. Hey, okay. So definition of conservation of electric charge. So again, this is like the idea is like if you have a system, if charge moves in, charge must move out as well. It's like the system must stay balanced. The idea of conservation. AP loves to emphasize this a lot. Like try to be in equilibrium as much as you possibly can. And then resistivity, that was not on the exam too much. It's like how resistive something is. Let's see. Oh, the capacitor stuff. Yeah, okay. I'm not qualified to talk about the capacitor stuff at all. I like completely just memorized that for the exam last year and then just forgot it ever since. But I can talk about resistivity and resistors because I've dealt with those before.
Resistors are easy.
Oh yeah, so okay. This equation, I like to think of it as replay. So it's I don't know why I think this. So it's REPLA. So it's a replay. So it's basically what is this row? So this is the resistivity times the length, right? I'm pretty sure it's length. Yeah, length over the area of the resistor is equal to the resistance of the resistor. So I mean, you just need to know how variables work in that. All right. Resistance and capacitance. Okay, resistance I can talk about. Capacitance I can't. So V is equal to IR. That is our classic Ohm's law. And basically the voltage or the amount of voltage dropped, or how I like to think about voltage, first of all, that's very confusing. Think of it as like potential energy, but for charges. That's basically what it is. So when you be like voltage drops from one place to another, that means like electricity has been provided and then like the potential energy of the charge is lost. And then in return, it's providing electricity. That's how I like to think about voltage. So let's say we have like a 12 voltage drop from one spot to another. Let's say there's a resistor of 2 ohms, right? Then therefore the current, that would be 6 amps. So yeah, that's an amps right there. That's current in amps. So that's good to know, like voltage drops, like understanding what voltage truly means. I highly recommend searching up what voltage is. It'll help for this unit a lot. So that's that over there. Capacitance. Okay, do I have to talk about capacitance? All right. Do you guys know anything about capacitance? Because I like completely forgot what a I know capacitors. They're also, I think of them as like batteries, where they store energy. Yeah, they store electrical energy, but there's like special rules to capacitors as well. Do you guys remember them?
It like started off uncharged and then they like charged up like on their own or something. I forgot.
Yeah, so doesn't it like act like as if there isn't?
It's like a budget battery. That's why.
So it's just like a wire.
Yeah, it's like I know they store energy. And then a
There's
specific
something about the plates being a certain distance apart. Something.
Yeah, I'm just gonna be searching up capacitors here. Capacitors.
Ooh.
Yeah, so it's devices that I just need to remember what a polar. Oh my god, everything is coming back together. So we have polarized.
Polarized.
Yeah, I know they can be polarized, but capacitor.
Did they
Okay,
ask?
wait. I think this is how capacitors. Oh yeah, so then capacitors they work like this. So like they have something over here. We go from negative. So they have a negative end to positive end. So basically, what a capacitor does is there's some source that's bringing electron all the way to the positive side. Oh yeah, there's like this material in here that like prevents electron from going positive and negative. But essentially, there's a source of electrical energy that goes to the positive side. So that's causing it to increase in voltage. So it's increasing the potential energy. But then the capacitor has a limit. The capacitor has a limit on how much it can provide. Then once it reaches that maximum limit, then it's able to provide as if it was a battery. So that's what a capacitor is. Okay. But yeah, I remember I had an FRQ on capacity. I don't really know how that because I remember, okay, let me recall what I had in my FRQ. So I remember there was a capacitors question. Capacitors question. Like that was like, I think that was the QQT.
Ooh. Okay.
I think that it was the QQT, capacitors. Then I had one question. It was just purely optics. That might have been the short answer one. I don't know. I know I had a thermodynamic question for the paragraph short answer. And then I think another one might have just been like electricity or something. I don't think so. I had fluids. I don't think so. I had modern physics on my FRQ. But yeah,
Modern physics, that would not be it.
modern. Okay, honestly,
Especially
modern
like
physics, I don't know, just something with modern physics made it click for me. I don't know why, but compared to the unit 6 had a lot more information. But we'll get to that later. We're getting off track here.
I don't know. Did we even do the slit experience? Actually, no, I think we did.
Oh,
I don't remember
the
that
young
thing.
split. Oh my
And
god.
it's like these FRQs with like these weird lines and stuff. I mean, not lines, but they're like
Yeah, that's crazy.
it makes those gaps because of the interference and stuff like that.
Yeah. I don't think so. I'll be able to cover that level of difficulty.
Like two plates close together and it stores charge.
Yes, that's what capacitor is.
And the closer it is, the higher the capacitance is.
Yeah.
Mm-hmm. Oh yeah, that's right here, right?
Yeah.
Capacitance. Oh, this equation right here. So the closer the plates are, the capacitor plates are in storing charge, the greater the capacitance, the greater the area, the more charge they can store on the capacitor. Everything coming back now. Oh my god. But what is it? We're increasing the area, then we're increasing capacitance. Yeah. So again, it's just like with capacitance, you have to just relate equations, relate variables to each other. If there's an increase in one, what happens to another variable, so on and so forth.
I've never seen the equation under that. Like the E equals a Q over, is that epsilon?
Yeah, epsilon. This is EMF. Yeah, okay, don't worry about that. I really didn't understand what this was. It's fine.
And that's an epsilon.
What is epsilon? It's the electromagnetic.
That is an epsilon.
Yeah.
But that one's like a constant, right? Like they give you the constant.
Yeah, they'll give you the constant. The main thing to worry about is area and then same thing here. I think this is for a capacitor. I think the electric field of the capacitor.
Oh. Okay, yeah, that makes sense.
Yeah, this is for like resistors or just like in general of the entire circuit, and this is for capacitors in general.
Okay.
And then this is the potential energy stored by capacitors. Yeah, that's the potential energy stored by capacitors.
Are there a lot of questions on capacitors or?
Not too much. I don't, for some reason my FRQ had them and I knew what they were then. I don't really know what they are now, unfortunately. But I don't expect like the exam is like pretty evenly divided, honestly. But yeah, I think it's a good idea to like refresh on capacitors because it is quite a decent part of Unit 4. So
Okay.
Yeah.
We did capacitors in Unit 3 for some reason, right?
that should have not happened because electric 3, why did I say electric
We
3?
didn't do anything like other than Ohm's law and like the loops in Unit 4.
Oh,
thing-
loops. No.
Oh yeah, the loops are the
Like what's
Kirchhoff loop rule or
Kirchhoff's
something.
loose. Yep, exactly.
Kirchhoff
So,
voltage law.
Oh
essentially,
yeah,
okay.
and then power is equal
KPL,
to
KPL.
I times delta
power?
voltage.
Yeah. There's like
And
3
then
different versions of power.
Oh yeah.
the standard V equals to IR is the other one. But that could be physics 1.
So, okay, let's just make the transition into here. So there's 2 types of circuits. There's series circuits and then there's parallel circuits. I
Oh.
think
Oh, and
So-
then there's conductance, which is 1/R. Yeah.
Conduct. Wait, what?
Wait, what? I'm sorry.
Yeah.
So there's parallel.
Because like it's like the inverse of resistance.
Oh, I see what you're saying.
Oh yeah, you're right. The lower the resistance, the higher the conductivity. I mean, that's
Yeah.
the relationship you need to know there. All right. So here, I know in the series circuit, right? In series, the total resistance is equal to R1 plus R2. But then in parallel, it's like 1 over the equivalent resistance equal to 1 over R1 plus 1 over R2, and so on and so forth. That's for parallel.
That's Kirchhoff's loop rule. I forgot what it
Yeah,
was.
Kirchhoff's loop rule. Yeah, because it comes under the idea that charge must be conserved. So it's like if you have lower resistance here, let's say you have 2 ohms of resistance here, and you have 4 ohms of resistance there. There's going to be more charge going to the 2 ohm resistor than the 4 ohm resistor.
Yeah.
Then you calculate the charge going through all of those, and then based on that, you'll be able to determine the equivalent resistance. So that's how these rules have been formed. It's because the idea of conservation of charge, well, the amount of charge that goes in, if there's 6 amps of charge that goes in total, and there's 2 amps that goes into here, then therefore there must be 4 amps that go in there. I mean, this is not a good example because of these numbers right over here, but it's the idea that they're trying to provide. So it's like the total charge that goes in is equal to the total charge that goes out, essentially.
Yeah, it says the delta voltage is 0.
Yeah, delta voltage. I mean,
Wait, what?
no, the delta voltage as it goes from one side to another side.
Is not.
1 loop,
The-
2 loop, and 3 loop.
It's like the change in voltage as it.
Oh, sorry. What does it say? The
I think
sum
it's
of
the-
voltage difference around the circuit loop is 0.
Okay.
Hmm,
Oh, it's because
yeah.
it's like
Oh, you're talking about that.
okay, yeah, that makes sense.
Because it starts with the battery and then like the resistors and all of that. And that's equal to 0.
Yep. All right. Oh, these are all the ohms laws. Okay, I didn't see this at the bottom. So, this is in series. So if you're in a series circuit, then the resistance is all equal to all of that over there. You can parallel this thing. It's right there. If you have capacitors, then it's actually the opposite. So if you have capacitors in parallel, then you have to add all the capacitors together, capacitances together in order to get the total capacitance if it's in parallel. But if in series, then you got to do 1 over the capacitance. So then, I mean, these are all the equations, and it's pretty confusing to be honest, but you have these on the equation
Equation
sheet.
sheet.
Yeah, and
Wait,
as you see,
See on the capacitance ones? Because like
like, should you know these? Like,
I mean like
watch-
obviously you should, but like did you get any questions on those? Because like I've never oh my
I
god. Sorry.
don't think so. They come up that much. Yeah, I don't think so. They come up with that much, but yeah, it's definitely good to know.
Okay.
All right.
So
I
we
think
just
we're-
finished the whole unit.
yeah,
Okay.
yeah. Pretty much, we talked about the entire thing that we need to know for unit 4. So let's move on to.
Ugh,
Oh no.
Oh no. Okay.
flux, don't even get me.
Magnetic flux. All right. See, as we go through the units, my knowledge decreases, but it's all right. Okay, so magnetic systems. It took me a moment to realize that magnetism is an actual thing. For the longest time, I thought electricity and magnetism were the same. but they're not. So magnet is like magnetic attraction. I don't know how to explain magnetic attraction, but it's there, right? So I think the big thing with magnetism is there's three things. There's the magnetic field that acts in one direction. There's the current, or we can just say the force acting in one direction. And then let's say it's either a velocity or a current in third direction. So basically what we have is the good old right hand rule. So it's basically if you have the force on one, if you know the direction of the force and you know the direction of magnetic field, then you just point them with your right hand and then you can determine. So let's say the force is like leftward and the force is leftward and the velocity of a particle is upward, then the magnetic field, if you like point your other three fingers inward, that means it's into the screen. I get confused. So yeah, in is into the screen and then out is outwards of the screen. For example, if you have like a screen right in front of you. So that's the right hand rule over there. Magnetic permeability and magnetic dipole moment don't really appear on the AP exam that much, so I'm not going to worry about that. Monopole versus dipole. I'm pretty sure like monopole is like, okay, if you have like one field over here, then what is it? You just have one field over there. But if you have like, let's say you have a magnetic bar, for instance, you have north and south, then the magnetic field, what it would do is it circle around. It would go point away from north and it'll point towards the south. So that's what, that's a dipole. So like when you're dealing with dipoles, then magnetic fields occur in circles. Yes.
And the actual B field is like tangent to the lines, B field lines, right?
So you mean the force?
Yeah.
Yeah, the forces would be, it would be perpendicular in one component. And then, yeah. So basically magnetism, everything is perpendicular to each other. If you really think about it, there's nothing parallel to each other. So that's a good thing actually. So if there's like a magnetic field and a velocity pointing the same direction, then there would be no force acting. So if two things are parallel to each other, that means the third thing does not exist. You can use that to your advantage. I mean, that's more of a math thing, but also applies to physics here as well. Oh, there's another thing, the current. So let's just say we have a pole, not a pole, a wire, right? And then there's current going this way. There's current going this way. That means the magnetic field. So you take, I forgot it was, if it
You
was
take your right
hand.
hand and then you wrap it around and your thumb points in the direction of the current. And then like your fingers are where the B field is.
My question is, do you use the right hand for that or your left hand?
I think it's right,
You're
yeah.
all right.
All right, I think.
I remember from physics 2, there was something that was left hand. I don't remember what it was. I don't know what it was. Okay, but if this is right hand, I'm just gonna stick with right hand. Let's hope for the best. Okay, you guys are taking the class. You guys.
There's
So,
the
yeah.
Fleming's left-hand rule.
Yeah. What is that?
I don't even know.
I want to know.
Yeah, no, actually it's good because I don't want to get confused. So, I mean, left.
Mm.
Motion of.
Oh, that's like the same thing, except
That's where we like, that was like the palm one. That's where we're here.
the palm one. I don't even remember the palm one. One like, oh, the motor. Oh my god, I failed that question.
We all did.
Yeah, no one even like remember the video. He's just like, guys, watch this video and you'll know.
I legit just guessed on like all the direction ones.
Yeah, I was just like, it's okay.
Yeah, I mean, I guess.
To know the motors and stuff. I mean, like I've never seen a motor question.
Yeah, I've never seen a motor question go on the EP exam, but they will have questions where they have like they show you a magnetic field. It'll be like, I think, okay, please correct me if I'm wrong, but X's are outward and dots are in, right? Or is it the other way around?
Oh no, X's are in. Yeah.
Oh, X's are in, so
Wait, what?
okay.
Wait, no.
There's no way. No, wait. I think. Wait, no.
Okay, so gotta search this now.
Let's just go through all the
Why?
right hand rules.
X outward.
Oh yeah, then there's a second right hand rule where the thumb is in the
My God.
current direction, fingers are the magnetic field, and your palm is the force.
I think you have to say magnetism. But
Yeah, magnetism.
wait, actually, is inward like X?
Oh yeah.
Yeah.
Yeah, right.
And
Okay,
then
let's remove this. We say X's are inward and dots are outward. All right. So yeah, they'll have questions like this where they have this magnetic field and they'll have like something that enters the magnetic field. Oh, this is where you have the change in magnetic flux. Yeah.
Oh no.
I remember this. So it's like when magnetic flux refers to okay, I have to go back to this equation. Yeah, this is the
It's
electromotive
times
force,
area.
right? Yeah. So
Yeah, there it is.
it's B times area, but the change in magnetic flux means what is
Delta
it?
flux was something with current, yeah.
Yeah, basically.
Oh, that was the third one where like the current, it was like this, like your finger was where the B field is pointing. No, your thumb was where the B fields are pointing. Your fingers were the current. And no. Yeah. So you had a current, right? Then there's a magnetic flux in one of the directions. And then you had to oppose the magnetic flux.
Yes.
And then the current was the way your fingers were.
Yep. That was the I think that was left hand. Or I don't, it was definitely a hand rule, but I remember, yeah. So if there's a current in one direction, it's a good point. All electric currents produce a magnetic field. So here there will be a magnetic field over here. That means what is it? That means if there's a magnetic field over here, and then you can use the other right hand rule to determine the force in specific direction. So here the force would be downward or something. Here the force would be upward. So like in opposing parts of the magnetic field, because they point in opposite direction, then the force would also be opposing as well. So there's that there. Over here are the equations for magnetic field. So you see it's dependent on three things: the velocity of a charge, the actual charge itself, and the magnetic field. And these are all vectors. If they point in all three different directions, then you have a magnetic field. And oh yeah, over here we see that the magnitude of this, it's a cross product. That's why they have this cross over here. It's a cross product of the charge, the velocity, and magnetic field. And then this is for current carrying wires over here, IOB sine theta. Yeah, so there's two separate instances where magnetism occurs. So you got to know for this for moving particles and here for current carrying wires. All right. Is there anything else that I need to cover here?
wait, sorry, I had to head out for a bit, like, because my
All right.
brother started playing. No, like I had to come upstairs because my brother started playing the piano, like literally in the random. But
All
it's
right,
okay.
no worries.
Can you go over flux if you didn't go over that?
Yeah.
Okay, thank you.
So flux. So change in magnetic flux. I have to remember what EMF is back in the EMF is, yeah, it's an electromotive force. So EMF is basically defined as it's a change in magnetic flux, the negative change in magnetic flux over the change in time. So essentially what it's trying to say is, okay, I think, oh yeah, electric motive force, that's voltage. Yeah. Okay. So it's basically saying whenever, let's say you have a magnetic field right here. So we have magnetic field right here. And we have this box that's entering this magnetic field right over here. This charge, let's say it has like a negative charge, for example. Right? This negative charge. So then the thing is, let's say it's moving at a constant velocity of v. So when this thing enters over here, let's say it's halfway in and it's still moving. When it moves into the magnetic field, when there's a change in the area of the particle entering the magnetic field, then there's going to be a change in this area over here, which is changing magnetic flux. And changing magnetic flux means that there's going to be a voltage that's produced when that particle enters the magnetic field. But then, however, once it's fully inside, there is no change of that area in the magnetic field. So the magnetic flux will be zero, and the amount of voltage carried will also be zero as well. So that's the idea of magnetic flux, and that's the only thing you should really understand for magnetic flux. I haven't seen it in any other way on the exam.
Okay.
Okay, so it's magnetic field times area essentially. You just need to know that a change in the magnetic flux produces a voltage, and then a voltage that allows for current to go through. So that's why the motor stuff occurs the way they do, right? It's because they're having a constant change in the area.
Okay, that makes sense.
Yeah, so they have the constant change in area of like, okay, so like a motor, if it's traveling around an electric field this way, then there's going to be a change in the amount of area in the electric field. And it doesn't matter necessarily like how the electric field is, whatever, as long as you're changing the area, you're going to be producing a voltage. So and then that voltage creates current, which creates its own magnetic flux. And that's why there's so many different connections here. So that's why I think that's the only reason why magnetic flux is important. But other than that, yeah, just know that magnetic flux produces voltage. There we go. Easy and simple as that. And I think we have basically covered magnetism. I mean,
Are there a lot of magnetism questions on the test?
over here it says 10 to 12% weighting.
That's not too much.
It's not too much actually, but again, 3, 4, and 5 are very interconnected. So there's probably more stuff that's going to be dealing with electricity, but keep in mind that they will combine these 3 as much as they possibly can. At least I think, or maybe it's either 3 and 5 or 4 and 5 or 3 and 4, sometimes all 3. But I see these 3 being related to each other. So they have to be on the lookout for them.
Okay.
All right. My personal favorite. When I mean personal favorite, I mean the one that I do not like, waves. And geometric and physical optics. Now here I am completely clueless as to what these are. Okay, waves, electromagnetic waves. The only thing I remember from waves here, if I look at the equations, I might remember back then. But
I feel like I know the equations, but I don't know like the theory. So
oh, okay. So here's next thing. Lambda times frequency equals velocity of a wave. Okay, this makes so if you have a wave, right, and you have this wavelength multiplied by frequency, I think frequency is referring to like how often it oscillates, right? The more often it oscillates, the faster the wave seems to go, and like the slower it oscillates, right? Then like that's like there's a smaller frequency, there's less amount of like waves that are traversing per second. Then yeah, the velocity would decrease. So I think that's that equation right over there. And then everything from here on out, this is over here. Let's see.
Wait, for magnetism, did we cover Faraday's law?
Faraday's. Isn't that the change in? Isn't that the change in flux?
Okay,
right? Yeah, that's Faraday's law. That's what we keep. Okay, yeah, that's Faraday's law. So
yeah,
I just know that change in magnetic flux provides voltage. That's all it is. This is the index of refraction thing that I keep getting myself confused over, but it's basically saying the velocity. Okay, someone help me over here. This is the speed of light. And then this is the velocity, but what is this velocity referring to? This is index of refraction.
is it like the speed of whatever through?
Oh yeah, the speed of yeah. So like the speed of light. So that's why, yeah, whenever light travels, now it can't be, 'cause I know like index of refraction just refers to like surfaces, right? So it's just like if specific surfaces have specific different. Oh, it's like what's the velocity of something when it enters a specific substance or something?
Yeah, something like that.
Okay, so I think
like-
that's what it means.
Material itself. Like if you know the index of refraction, like I think
You can determine the velocity. Ah, I see.
velocity, yeah.
Okay, so yeah, they usually give you the index of refraction. I never like solved for one, so that makes a lot more sense. So you have the speed of light, and you divide by the index of refraction. That gives you the velocity of, I guess, a
Something.
particle that goes through a surface. All right, and then Snell's law. Yeah, the fact that I know that Snell's law is pretty surprising, but it's basically referring to how light travels through different surfaces. So I remember it's like if light travels here, what you have to look at is you have to look at the perpendicular. It's the angle between the perpendicular and where the light is going. So it's this angle and this angle. So this would be our theta 1 and theta 2. And then based on that, you can get the index of refraction. If you have n1 over here, then you can find the index of refraction for there. That's Snell's law in the basic nutshell over here.
And usually like they make N1 like something easy like air. So
Yeah, exactly. And then yeah, air is in that one.
yeah, air is one.
Air is one. Yeah, okay, makes sense. So then yeah, you can like manipulate this equation around. Yeah, again, physics is like mostly a lot of the time you don't need to know like what's behind it. If you understand how to manipulate equations, you're probably good enough. But yeah, that's that case. Here we have, okay, I need a reminder on what this equation represents.
That's the lenses.
Oh, yeah, okay, isn't it? Okay, so then now, okay, we have something over here. Then these are the ray diagrams, right?
Oh, wait, we forgot to go over total internal reflection, whatever that was.
Total internal reflection.
That's one.
I'm blanking.
One of the angles is 90.
Oh, so
Like
Oh yeah. So sine theta c, which I think is the angle needed, is equal to what?
so like this. So it's
yeah. Because sine of 90 is one.
sine of 90.
Sine
So
theta equals n2 over n1 is what I'm seeing.
I mean, did they do that? Like, did you find
Yeah.
out?
Basically.
okay, I know like. Oh yeah, aren't there like instances where like what is it? Sometimes it's absorbed
Like it
in one
bounces
way,
back.
and sometimes. Oh yeah, like light always reflects off the surface, right? And then it's just like whatever refracts. So this is the one of it is reflection, right? This is reflection, it just bounces off, like waves it just bounce out. And the other is refraction. And so like that's what enters the surface. So I think what Pranay is trying to say is like the point where like none of the thing is either refracted or none of the light is reflected.
Yeah.
Yeah. Wait, what was that called? It was total
Total
Reflect-
internal reflection.
total internal reflection. So let's just search it up. Total.
Yeah, I think that's just the theta one is 0, right? I mean 90.
Probably.
Or ooh.
Physics tutorial. Oh yeah.
Yeah, it's
When
when
the
none of it escapes since it's all dead.
Oh,
angle of incidence, angle, critical angle. Yeah.
okay. I see.
Here. So yeah. So it just bounces off. It just only does reflection. So it just bounces off. So there's like none of it that goes. Is it? Yeah. Oh, that's where it is. It's the critical angle. So angle of incidence. So like the angle that enters is 90 degrees. So okay, so this what is this? Theta 2 is equal to 90 degrees. Then what is it? Angle of refraction is also 90 degrees. But then once you go to an angle greater than that, greater than this angle of incidence, then from the perpendicular, right? So here's the perpendicular. So then once you go away, as you see this one's going a little bit more, then it completely reflects. But let's say you're less than 90, so like you come somewhere around here, for instance. then what is it? Then you're gonna have refraction. But then there's this angle right here, angle of incidence, where it's like the angle of refraction is exactly 90 degrees, and then once you go over that, then there's no component left to be refracted, so everything gets reflected back. That's the idea. All right, let's go back to this right over here. This is lenses, yes. I remember you had
You spent
something.
so. Oh my God. I did not like this unit.
Yeah, no, this was one of my least favorite ones. I liked Unit 7 a lot more, but there's a,
Well, like the ray diagrams for the AP test, like it would, let's say
Well,
got
you
that.
have to draw ray diagrams.
my test did, because I
Oh.
took the second administration because there was multiple administrations last time, so I had to draw a ray diagram.
Okay, so like
What?
one of them through the center, I know that. And then
Yeah, so what the object?
converging, but like for the other ones, I just have no idea.
Okay, yeah. So I think there's 3 points to draw a ray diagram from. There's one that goes directly through.
One goes straight parallel and then goes through the focal point on the other side. One
Mhm.
just goes completely straight through and like doesn't change. And then one goes through focal point on the left side and then goes parallel out on the right side.
Yes. And oh yeah.
And there's this thing where either S prime will like sometimes be negative when like it's a virtual image.
Oh yeah, virtual images. Yeah. So like, virtual image is like something that you expect on the same side, but it doesn't appear. That's the case over there. Okay, so okay.
That's a
there's
lot
two
of
po- That is a lot of line. I mean,
Oh,
difficulty
I see what it
to
is.
show how all of the things would appear on the same instance over here. Okay, so one thing that goes through, it goes parallel and then goes through the focal point, one times the focal point. Oh, and the focal point is, oh yeah, there's like some types of instances, right? Like if the image is 2 times away from the focal point, or like in between the focal point and 2 times the focal point, or like sometimes it's even inside the focal point, right?
Wait, it is a virtual image, right? I think that one's.
Yeah, okay, like if we
So for
draw.
like converging lenses, if the object location is double the focal length, then we get like a real inverted reduced image, which is like a camera basically. If it's in between 2 focal point lengths and 1 focal length, it's a real inverted enlarged image, like a projector basically. And if it's inside the focal point, then it's virtual upright enlarged like a magnifying glass.
Wait, isn't this for converging or?
Those are for converging. I don't want to go.
And then for diverging, they're all virtual, right?
Yeah, they're all virtual. And yeah.
Oh yeah,
they're all virtual and they're all upright.
yeah, I guess for ray diagrams, I think the best thing to do, at least, is to remember to draw from 3 points. For a converging lens, yeah, one you draw parallel and then through the focal point. Second, you just draw through the, I guess you call it the 0 eye. You just go straight through, and then the third point is like you draw
Through the.
okay. Yeah, you draw through the focal point. Okay, this is a terrible image. Let's find here. Yeah, here you draw through the focal point of one side of the side you're currently on, and then parallel afterwards. And then that will give you your image. And then based on that, real image comes on the other side of the lens, and a virtual image comes on the same side of the lens. So you don't necessarily need to like memorize. Yeah, go ahead.
You have to do those like little dashes to like find where they intersect.
Oh,
So
yeah.
Everyone's virtual.
Oh, actually, I think over here on the red hand side, I think those would be dashes, right? Because or something or that. I know something would be dashes. Oh, here. Oh, this is. Oh, if it was a virtual image. Okay, if it was a virtual image, then you have to draw dashes because technically light isn't traveling in that direction. Or like, no, yeah, the light's not traveling in that direction, so that's the case over there.
Okay.
So this formula is just like, okay, this formula is just basically, what is it? This is the eye is the image, and O is the object. Yeah, now that gives you 1 over the focal point right over there. So this calculation will give you the like the focal point, all the stuff. Then once you have that over there, then you need to do the physics behind everything, and then you need to draw the angle of the angles for all of that.
Then there was like linear and like non-linear magnification. Is that on the test?
I don't think
No, that's probably not. Just
linear.
just
There's-
linear.
Yeah, I don't think there's angular because like
Yeah, that's too much.
Uh,
This is the splitting experiment thing.
the what? Oh yeah, that's the. I know how to use the second one, but like I've never seen the first one.
Yeah, I don't think so. Honestly, don't worry. If you get a split, just
Because
I
I've
mean,
seen, like the
yeah, go
split one on every single like
test. Yeah. So D sine. This is like referring to like splits, I think. Yes, let's pull it up. D sine theta is equal to m lambda. Fun way.
Whoa.
Interference.
Yeah, and it's like lighter and darker in some places.
Yeah, okay, superposition. So it's like a bunch of light adding up to each other. So they all have the same length. So it's just like this part of the light that's entering a split. So it's like D sine theta. That's what this is right over here. And then the actual wave itself is the M. Does M stand for? Okay. Does M actually stand for?
M is
mass?
magnification.
Oh, magnification. Why is it lowercase?
Capital, lowercase is mass.
No, that's an
Oh,
integer.
it's just an integer.
Bro,
Wait, that's not very helpful.
That's not being helpful at all. But
They don't want you using it. You are supposed to memorize it.
mhm.
Oh wait, integer meaning like because doesn't it only like do the stuff if it's like a multiple of the wavelength? Like
Yeah. I think. Oh yeah. That's why it's an integer specifically. That's a good.
so like
good-
honestly, if they give you a question, would the M even matter? Because like usually it's talking about like the manipulating either the wavelength or the distance.
Yeah, exactly. So then, yeah, I don't think so. That would really matter.
And it wouldn't matter as much.
Okay.
Yeah.
Okay.
However, yeah, okay. So now this is,
They
but
won't make the big FRQs about modern. I mean, no, this is so.
I don't remember if there might have been one question on this. I don't really remember too much about this. So there's that.
learn this, but okay.
Oh, you
Yeah.
guys didn't learn? Oh, okay. And okay, I mean, you can search up Young's experiment, double slit experiment, and like try to find videos on that. I think there's some videos out there that do a really good job of explaining what this experiment is and like how they figured this out. But I'm done with optics. Did we cover? I think we covered it. Okay, interference and diffraction. Yeah, that's not really on there as much. Images, these come up a lot. Refraction, yeah, those come up. That was the N1, N2. N1 sin theta equals N2 sin theta. Periodic waves. What are periodic? Periodic waves are just how waves that occur.
Oh, can you
Constant.
talk about the difference between the waves? Because like I know, are they mechanical waves? I don't know.
Oh, is it like
Those like
transverse waves?
yeah, like for mechanical, you need to go through like because they're like sound waves, you have to go through something. But then like electromagnetic waves, you don't have to go through anything.
Okay, let me see if that reading my electromagnetic wave.
Because like you can't hear like sound in space. That's why.
Yeah.
Oh. Oh,
Yeah, light is electromagnetic. Light is an EM wave.
Yeah. Electromagnetic. Oh, so it's like longitudinal and then transverse. Okay, so yeah, that's the difference, I guess. With electromagnetic. Yeah, so electromagnetic waves are light waves and they're transverse. And the sound waves. Oh, sound waves are not transverse waves. Those are I'm pretty sure they're longitudinal waves. Are sound longitudinal? Yes. Okay. So yeah, they move slightly different. So
They're
I
like,
think
They have to go through in a material or something.
yeah.
yeah. So okay, wave from pale. Okay. But I don't think so they appear that much in these. I don't really remember that much for at least those different types of waves at least. So we're good there. I'm just doing for this exam, just seeing okay, what's being covered, what's going to be covered, and what's not going to be covered. All right. Let's go to modern physics.
Hey, we gotta look at the EM spectrum.
Yes.
Oh yeah, so this one is like okay,
Yeah,
we look at like strong.
red is longer wavelength, but like shorter frequency or something. Yeah.
Infrared, yeah.
Yeah, yeah.
Longer
I think
wavelengths.
I was
For-
never like which order. Like, is it blue that has a smaller
Blue
wavelength?
has blue is the biggest frequency, I think.
Okay, so
Yeah, or violet.
Wait, someone just Google it real quick.
Yeah, it's just the colors of the rainbow, right? So you have infrared on one side, and then you have ultraviolet on the other side. So ultraviolet is high frequency, a lot of energy. So actually, right, I think it's perfect transition over here. E is equal to H times F, right? So ultraviolet has a higher frequency, so therefore it can that electromagnetic wave is what's it, purple, right? Then it would be will have a greater energy than if it has like infrared, for example. Okay, so another thing, okay, so this equation right here, the kinetic energy max, similar. So if you have a greater frequency, that means if you remember from this question right here, I mean lambda is equal to velocity times frequency, right? So actually that's pretty useless. But
Isn't
over
electric.
oh sorry, it's useless in the sense that it's not for this is for waves. I mean, here's also a wave too, but we have this equation right here. So energy is basically think of that as like partially kinetic energy. And then this not okay, this is the work function. So like whenever light enters like a specific material, there's like a specific work function. So like let's say there's light hitting the surface, that's like light. And then in order for light to be like emitted back, or like in order for like to bounce off at least, there's like some sort of like barrier. So let's say this is 2 joules of barrier. Then like you have 1 joule of light entering here, but like there's 2 joules required in order for it to be excited or something. I think that's what the idea behind this is then the light won't bounce back off, or there won't be like photons that like get jumped out essentially. And yeah, so there won't be kinetic energy to like particles. But let's say there's 3 joules now, then there'll be kinetic energy. I think particles will like move out the surface. That's pretty cool, pretty interesting. And then this one, I remember this question, H over P, it's named after somebody. I forgot who it was though.
It was just something. No.
No, wait, what was his name?
H
I
over
don't have to
P.
pronounce it. Yeah, de Broglie or something.
Oh yeah, de Broglie.
Yeah, de Broglie.
Uh-huh.
Yeah.
Right. So here, okay, how are they comparing this?
It's momentum. So like all the particles also have like momentum. Like that.
Yeah,
Yeah, all
so
particles have momentum, but some of them don't have mass, and that's where E equals m squared comes in, I think.
Yeah.
oh yeah. So wasn't there? Oh, isn't it like all again? This is like the wave form of energy, one of the, and then the other one E is equal to mc squared. It's like mass contains waves. Oh, it's like anything that has momentum has a wavelength. That's what it was. It was actually pretty fascinating discovery. So any object that has momentum has a wavelength, and they made the connection is wave particle duality, where they connected where all objects that have momentum, or yeah, all objects that have mass also have a wavelength. I'm pretty sure that's the idea behind it. So H over mv.
And usually they make VC, right?
Yeah, usually make V equals C. So it's MC. Yeah, okay, cool. And then we have our solid equals E equals to MC squared. I wrote this already. But like whenever you have an energy, okay, so like whenever energy like breaks off, right? Or if mass breaks off to some sort of thing, then that remaining thing is converted into energy. That's the idea behind it. So whenever you see like energy equations, think about conversion. So like say there's an increase in energy, then means there's also an increase in mass as well. If there's a decrease in energy, like some mass has been gone due to like an explosion, then the energy of the system will decrease. So that's the idea behind it. Let's go back to the CED and see. Yeah, mass energy equivalence right there. So anything that has mass, atomic mass has atomic energy. That's the idea right there. Radioactive decay.
That's just alpha is 4-2. Beta.
Oh,
I gotta talk about alpha beta.
Gamma 0. That's all. I
it's
think that's all they ask about. They don't like go into like. I mean, I'm
No, but
not
alpha particle. You need to know that alpha particles have atomic mass of 4, but they're like charged.
too.
It's like a helium particle or something. Yeah, that's good.
Yeah. So then, like, that's how you're adding mass onto there. And then similarly, you know, if you add a beta particle, you know, you're adding. Beta particles don't have any mass, right?
Yeah.
No. Okay.
Gamma like don't have any thing.
Exactly.
Is that the end? Like.
That is pretty much it. Photoelectric effect. Oh, photoelectric effect, the one I was talking about, like right here. Yeah, I was talking about the work function right here. So like, bounce. Yeah, that's the photoelectric.
Light to excite.
Yeah, you need, like there's a specific work function that you need there, and then once you counter that work function, then particles get excited and then they move, and that's kinetic energy in that form. Properties of waves and particles. I think here they're just trying to show that okay, anything that has mass has moves around, and that is pretty much it. Wave functions probably like rarely show up on the exam, so don't need to worry about that. So that is pretty much it in terms of like content. I do have a few slides in terms of like key tips. Here, I'll just. So for physics 2 at least, the big stuff that you need to know is ideal gas law, Kirchhoff's loop rules, Snell's law, E equals mc squared, and then there's a bunch of other equations that we looked at right now. What is it? E is equal to hf. What is it? The capacitor equations, the resistor equations. Just understand how they work the way they do. You just search up like Kirchhoff's loop rules for those, and then you'll be able to understand the idea. If you understand the intuition behind all these equations, then like especially for the FRQ, you can employ those like use those as like, you know, your wild cards, and like you just employ those and then base everything around those, and then that's how you can score the maximum amount of points. So I included Newton's law of conservation of energy, conservation of momentum on here, but that's more physics 1. You could also energy and momentum can still be applied. Honestly, all of these can be applied for physics 2, if depending on the situation. Yes, if you're doing a fluid, so like a thermodynamics, then probably you have to draw a free body diagram and show like acceleration or something. That means not likely, but it's definitely possible. Like physics 2, your scope is expanded a whole lot more than physics 1. So there's something to be lookout for. You gotta be careful. You gotta remember some stuff from physics 1. They're not gonna ask like straight up physics 1 mechanics questions, but like the knowledge that you build from physics 1 will be similar to physics 2. That is very interesting.
Okay, well, I have to leave right now, but thank you so much.
Yeah, of course. I'll just go through this one.
Yeah.
Here.
Yeah, I have to.
Just one slide. All right. Okay. So key tips. Okay, if you're stuck on a question, then you got to think about what topics relate to the question. So if you know something, like anything about that question, you use multiple choice, write it down. So for example, if it's like a fluids question, like, and if it's like dealing with like fluids in motion, right? Then you can deal with what is it? You can just write down like Bernoulli's, for example. So if you do Bernoulli's and then you'll figure that information out really quickly. The formula sheet, yeah, sometimes it can be useless, but sometimes it can be really helpful as in terms of like, especially for physics 2, there's a lot more stuff that's a lot harder to memorize. So you could use that as a guide and you can manipulate this equations around. In terms of the multiple choice, you can do the math-based questions. So like, there's very little math on there, but like Bernoulli's equation might take up a lot of time. And considering that you only have 90 minutes for 50 questions, you want to be strategic on when you do those. And remember that topics might be like switched together. So for example, in physics 2, electrostatic circuits and magnetism, they could put a bunch of random questions together that go together, and they'll call it a day. And they'll say, okay, it covers this part, and this part of the CED, we're good. So that's what the AP graders would do in order for this exam. But that's how they to do the AP exam. And then just one really helpful tip that I can give is the AP daily videos. They're insanely boring, but they get the content and like the fundamentals down. Like the fundamentals, I wasn't able to like cover super in detail over here. It's just like an overall refresher. But those AP daily videos, those topic videos, they go into specific what each thing is. And for that, you can determine information super easily. And that is it. You guys have any questions? And I will end the meeting, right? I will end the recording right here.